Math 13-14, hypothesis test, population proportions. Testing the difference in two population proportions, the p-value approach. Before we jump into this example, I want to review the p-value approach steps and the formulas for the test statistic. First step, state the hypotheses, not a big surprise there. Second step is to calculate the test statistic, and let's just quickly review that formula. When testing the difference in two population proportions, your test statistic formula is z equals p hat 1 minus p hat 2 over the standard error, where the standard error is the square root of the sum of two fractions. The numerator of each fraction is the same, p bar times 1 minus p bar, but the denominators are the two sample sizes. And p bar is the pooled sample proportion, where we think of this as one sample from one population instead of two samples from two populations. All right, step one, state the hypotheses. Well, let's read the question first. A pharmaceutical company is testing two vaccines. Imagine that. In a group of 50 patients who received vaccine A, 80% saw improvement. In a group of 40 patients who received vaccine B, 75% saw improvement. This is not the question I want. Can we conclude vaccine A has a different success rate than vaccine B? All right, so let's start with our hypotheses. Null Alternative. The only statement even comparing the two success rates is the question, can we conclude that vaccine A has a different success rate than vaccine B? In other words, can we conclude that the proportion of people who take vaccine A and see improvement is different than the proportion of people who take vaccine B and see improvement? So we're being asked, can we conclude if PA is different from or not equal to PB? And since that does not allow equality, it has to be the alternative hypothesis. What's our null? Well, we really don't have a choice here. It has to be equal, because if it was either of the inequalities, like greater than or equal to, then it's possible for these to be true simultaneously. For example, in that situation, they're not equal, and this one is greater than or equal to that. And remember, when you're doing a hypothesis test, if one hypothesis is true, it forces the other one to be false. The only option here is to say equals. Left tail, right tail, or two-tail? This will be a two-tail test. And I'm sorry, after reviewing the test statistic formulas, I meant to go back here and continue summarizing the steps. So let's do that real quick. Calculate the test statistic, calculate the p-value, which is the area of the test statistic tail, double it if it's a two-tail test. Then we make a decision by comparing our p-value to our significance level. P-value less than the significance level, we reject the null hypothesis, otherwise we do not, and then we answer the question. All right, let's calculate our test statistic. This is going to take a little bit of work. Let's think about the order in which we need to do this. We can't calculate z until we know the standard error. We can't calculate the standard error until we know the pooled sample proportion. But there's even more missing information. As we saw in a video, the previous video, the pooled sample proportion is as if we looked at these 90 people together and saw what percent of them saw improvement. But the problem here is we weren't told how many of the 50 patients saw improvement, and we weren't told how many of the 40 patients saw improvement. We were only told the percentages. So if 80% of the first group saw improvement, how many was that? Well, that would just be 80% of 50. So before we even calculate the pooled proportion, we have to do a little bit more detective work, if you will. 80% of 50 is 40. Convert the 80% to a decimal and multiply. So 40 people saw improvement. With vaccine A. And similarly, 75% of 40 which is 30. 30 people saw improvement with vaccine B. And again, we need to know those specific numbers because we need them to calculate the pooled proportion. So our pooled proportion, if we put the two groups together, out of the 50 plus 40 people who receive vaccines, 40 plus 30 saw improvement. That's 70 out of 90. And I don't need a calculator for this because it's going to be 0.7 repeating, which is 4 decimal places would be 0.7778. So now that we've got this piece, now we can calculate the standard error. It's going to be a lengthy square root. I'm going to do myself a favor. I'm going to go ahead and calculate 1 minus this, so I don't have to write 1 minus here and here. This is pretty easy to calculate. It's 0.2222. If I subtract from 1. So our P bar is 0.7778. Our 1 minus P bar is 0.2222. That's the same for both numerators. And our denominators are the sample sizes, which were 50 and 40 respectively. So you can tell I'm quickly running out of room up here. Let's see what our standard error is. In case you're wondering how to do this in the calculator a little faster, I do a little bit of algebra. I factor out the matching numerators, which leaves 1 over 50 plus 1 over 40. 1 over 50 plus 1 over 40 equals, and then I just multiply by that numerator, times 0.7778 times 0.2222, and then I square root that final result. So to 4 decimal places, 0.0882. I'm going to erase the formulas over here and just finish it. So our Z is going to be the percent of vaccine A improvement patients minus the percent for vaccine B over the standard error. 80% saw improvement with vaccine A, so 0.80 minus 0.75 for the 75% who saw improvement with vaccine B over the standard error, 0.0882. And if we do that math, we get 0.5669. And that is our test statistic, but we're not done with it. I hope the amount of calculations with this formula aren't throwing you off. It's just chasing another formula. The new player is the p-bar. This is our test statistic, which means we're done with step 2. So what is step 3? Calculate the p-value. And remember, the p-value is essentially the area of the tail cut off by the test statistic. So I need to make some room here because I don't want to lose my hypotheses. If you're writing that down, well, you're watching the video on YouTube. Pause it, back it up, write it down, then continue. Step 3 is to calculate our p-value. The p-value is the area of the tail or tails cut off by the test statistic. This test statistic being positive will be to the right of center, z equals. But because we're going to use our z-chart, we really only need that z-score to 2 decimal places, so 0.57, and then we can figure out this area. So let me get to my z-chart. 0.57, go to the 0.5 row, go across to the 0.07 column, and there is an area to the left of 0.7157. 7157. But that's the left area, so the right area will be 1 minus 0.7517. Let me double check to make sure that was the correct area. Yep, 7157. Oh, 7157. Didn't sound right. So that area is going to be 0.2843. But even that's not our p-value. Because remember, you double that area if it's a two-tailed test. That means our p-value, this is why I prefer the critical value approach, our p-value is twice this, 0.2843, but even if I didn't double it, I would make the same decision. Let's see what this is, 0.5686. All right, so there's our p-value. Took us a while to get there. Oh, by the way, there are technologies that will instantly tell you what this p-value is. But being a theoretical mathematician and not an applied mathematician or statistician, to be honest with you, I don't like resorting to technology if I can avoid it. All right, so our p-value is fairly large. I'm a little bit taken aback by how close the p-value was to the test statistic, but I assure you that was total coincidence. All right, we're ready to make our decision. Step 4. We weren't given a significance level. So what do we assume? We assume a significance level of 5%, or 0.05 if you will. The p-value is about 56%. That's just a little bit more than 5%. And since our p-value exceeds our significance level, we do not reject the null hypothesis. So we don't reject the null hypothesis, we keep it and reject the alternative, and now we can answer the question, can we conclude vaccine A has a different success rate than vaccine B? We cannot. We were being asked if we can conclude the alternative hypothesis, so in short the answer is no. But in long the answer is no, we cannot conclude vaccine A has a different success rate than vaccine B based on this evidence. We blame the discrepancy on the samples picked, and not that the claim that the null hypothesis was wrong. All right, one more video, and this is going to summarize things because I know I've been all over the place, literally on the board. I'm over here, I'm over here, I'm over here, I'm down there, blah, blah, blah. But I want to clean things up nicely and wrap all this up.